How do objects fall? We know things fall to the Earth because of gravity. Why don't they constantly accelerate, as would be suggested by the single force of gravity acting on the object? After all, if these skydivers were falling at 9.8 meters a second, then they would be going at faster than the speed of sound when they hit the ground. Clearly they're not, so something else must be coming into play here. That something is air resistance, or drag. Common knowledge tells us that the drag force is in the opposite direction of the velocity of the moving object. But the question still remains of what the magnitude of the force of drag should be. By engaging in empirical observation and data analysis, we find that the magnitude of the drag force is proportional to the square of the speed. For now, though, we'll treat that as a hypothesis that we can prove by comparing our observed data with computational models, one including the force of gravity and the other including the force of gravity and drag. And then, once we've proven that drag does in fact have the qualities we attribute to it, we can examine the significance of this fact. So we'll compare the data from this video to the yield of our models. Both of our models are initialized with some of the same data. The ball's mass, which is taken from general information found on the internet, and the initial position and velocity of the ball, both being 0. Our first model has only the force of gravity considered, so the downward force, the weight force here, will be in the negative j hat direction, so in the negative y direction, with magnitude g times the mass of the ball, which comes out to be 9.8 meters a second squared. Furthermore, since the force of gravity is constant, the change in velocity is constant. And we run this model to see, as expected, a falling object. The position graph created is a parabolic arc, and the velocity graph is a straight line, as expected. Our second model includes the force of drag and is thus a bit more intricate. The weight and drag forces are added to give us our net force. The weight force is left unchanged, but the drag force is something entirely different. It points, as we said before, in the opposite direction of the velocity, multiplied by the magnitude of the velocity vector squared, so the speed squared. All of this is to say that the drag force becomes larger as the speed becomes larger. When we run the model for 0.5 seconds, we can't see an immediate change in the short time frame. But when we look at our graphs, the velocity versus time graph has an interesting curve to it. Instead of being linear, as it was in the first model, we see it curve upward. This is even more pronounced when we up the time interval and run the model for longer. Instead of saying straight, as it would with just the acceleration of gravity, it levels off to a sort of terminal velocity. It's important to note that this model isn't, strictly speaking, a prediction. The constant b was calculated by changing the value of b each time so that the final position would be equal to the final position of the observed data. In any case, we must give an account of this so-called terminal velocity. If we represent the constituent weight and drag forces with arrows and run the model, we see that as the model speeds up, the drag force gets larger, until they are both equal and the net force is approximately 0. That being said, the speed of the falling objects obviously does not become 0. They don't stop in midair. The change in velocity does, so that they're falling at a constant speed with 0 acceleration. So which model best represents our video data? As might be expected, when we look at the graph of time versus y position for our observations, the blue points, and our models, the red and green lines, the model with drag very closely matches the observations after about 0.25 seconds, whereas the model without drag diverges. This tells us that a model with drag force varying proportionally with the square of the speed is correct. Common knowledge tells us that drag is also probably dependent on other variables like air density and surface area for different objects. But for our specific example, we lump that in with our discussion of the variable b. Considering terminal velocity, though, it brings up some questions. What if the paper in our video was thrown downwards to begin with? Would the terminal velocity be greater or the same? Throwing an object down from a height only makes its drag force grow greater faster. It doesn't mean that the terminal velocity will change. We just change our initial velocity to say -2 and run the program. As before, the drag force grows large and counteracts the gravitational force. We observe the velocity of this graph starting out greater, but leveling off at about 6, the same terminal velocity we observed for our graph that was just dropped.